This video is about moments of random variables and moment generating functions. So suppose that x is a random variable. Then we define for each non-negative integer k, well, I guess for each positive integer k, the kth moment to be the expectation of x to the k. So this is called the kth moment of x. So when k is 1, it's just the expected value of x. And so if what this is the sum of x to the, say, j times the probability that x is equal to j from j equals 0 to infinity if x takes values from 0 to infinity. And if it's discrete, if it's continuous, then it's the integral of x to the k times the density function, right? Okay. And these could be calculated explicitly by using a formula, but we are going to introduce a function whose derivatives actually give you the moments. And that's called the moment generating function. So we define the function of t, phi x of t, to be the expectation of e to the t x. So this is called the moment generating function of x. And the reason why it's called the moment generating function is because of this theorem, which says, so suppose that your moment generating function, so it's a function of t, suppose that this is finite for t in some interval negative t0 to t0 for some positive number t0. So in other words, suppose that the moment generating function is finite on some interval containing 0, right? That's what this is saying. Some open interval containing 0. Then if you look at the kth derivative of phi, so this phi with the subscript, which is n in parentheses, right? It's not just phi to the n. It's phi with the parentheses n. That means the nth derivative, not, right? Without the parentheses, it would just be phi times itself. It would be a product of n phi's. But we're talking about the nth derivative evaluated at 0. That number is the nth moment of x. Okay. So let's just write on the side, this means the nth derivative of phi. So for example, suppose that x has an exponential distribution with parameter lambda. So recall that that means that the density function is lambda times e to the minus lambda x. Then the expectation, so we're calculating the moments, and we need to find the expectation of e to the tx, and that by definition, so this density function is only when x is greater than or equal to 0, right? So you integrate from 0 to infinity of e to the tx, that's t little x, lambda e to the minus lambda little x dx. So this e to the tx here is capitalized x, right? Okay. And then there's a theorem that says that this is equal to that. All right, now we calculate the integral, so we can pull out the lambda, right? So lambda times this integral, and then we can combine the terms. It's e to the negative parentheses lambda minus t x tx. Remember, we want to do this because we want to have an integral where it's e to the minus something. So when you do the integral, you get lambda over lambda minus t times the integral from well, we're doing the integral, I guess, e to the negative lambda minus tx, is that right? Yep, that's correct, because when you take the derivative of this, when you differentiate this function, this negative lambda minus t comes out, but then because of the chain rule, there's a minus here, so it works. So this evaluated from 0 to infinity, and then, so this is only when t is less than lambda, right? Because you need this thing to be negative in order for this integral to exist. And then when t is less than lambda, you're going to get 0 minus lambda over lambda minus t times e to the minus 0. Oh, did I get that wrong? Let's see. I don't see any mistakes. Oh wait, no, this is, you just have a constant here. So when you take the derivative, it's just going to be that constant comes out. So actually there should be a minus here. So there should be a plus here, and then you're going to get lambda over lambda minus t. That's correct. So that is that's the moment generating function, right? That's the moment generating function of x. Now to calculate the moments, we need to differentiate this function. So if you differentiate this function, actually we will look at the more general case. We will take the derivative of a more general distribution, which is the gamma distribution. Okay. So for instance, so more generally, if x has a gamma distribution with parameters n and lambda, so remember that in the case when n is 1, this reduces the exponential distribution. So the moment generating function, expectation of e to the tx, is the integral from 0 to infinity of e to the t little x, lambda to the n, x to the n minus 1 over n minus 1 factorial, e to the minus lambda x dx. Well, to do this integral, the trick is that we know that the gamma density function integrates to 1, right? So if you can make this integral look like the integral from a gamma density function, then you know that that integral is going to be 1. Now, what gamma density function should we have? So the thing is that we have an e to the minus lambda x and an e to the tx. So when you combine those, you're going to get e to the minus, okay, so you're going to get e to the minus parentheses lambda minus t x dx. And we have a lambda to the n, we have an x to the minus 1. So what you want to do is you want to make this look like a gamma n lambda minus t density. So let's just write out that density function. That's going to be lambda minus t to the nth power x to the n minus 1 over n minus 1 factorial, like this. So we know that this integral is going to be 1. Now what do you get on the outside? Well, we change the lambda to the n to lambda minus t to the n. So we have to have a lambda to the n over lambda minus t to the n out here. And we know that this integral is 1 because this is from a gamma n comma lambda minus t density. Right? So the density function integrates to 1. And so this is going to be lambda to the n over lambda minus t to the n. And this checks out with the previous example because we know that what we should get when n is 1 is the moment generating function of the exponential distribution, and when n is 1 you get exactly that. So this is the moment generating function of the gamma n lambda distribution. Okay, now let's calculate the moments of the gamma distribution. And then we will end up getting the moments of the exponential distribution by setting n equal to 1. Well, what we need to do, let's calculate the kth moment. We need to find the formula for the kth derivative of this guy. So let's call this phi x of t, right? Okay, so phi of t, we have phi of t is lambda to the n times lambda minus t to the negative nth power. And we need to take the kth derivative. Well, if you take the first derivative, you're going to get what? You're going to bring the negative n down, but then by the chain rule, there's a negative on the inside, so then you have to multiply, so then they cancel. So you get n times lambda to the n times lambda minus t to the negative, I'll write parentheses n plus 1. Right? It would be negative n minus 1, but I just want to leave it like this. So if you take the second derivative, what's going to happen? You're going to get an n, and then the n plus 1 is going to come down. Well, negative n plus 1 is going to come down, but then because of the chain rule, that negative sign gets canceled out. So then you're going to get n times n plus 1, lambda to the n, lambda minus t to the negative, parentheses n plus 2 power. And you just continue the pattern. If you take the kth derivative, you're going to get n times n plus 1 all the way to n plus k minus 1 times lambda to the nth power times lambda minus t to the negative parentheses n plus kth power. So the expectation of x to the kth power, remember the theorem says that this is just what you get when you plug in 0. Well, you're going to get n times n plus 1 all the way to n plus k minus 1 times lambda to n times lambda to the negative parentheses n plus k. And that's going to leave you with lambda to the minus k power. So let's just write it down. On the denominator, you're going to get this. So this is the kth moment of the gamma density function. So then for the moments of the exponential function, so in particular, if x has an exponential lambda distribution, then the kth moment is, well, when you plug in n equals 1, you get in the numerator the product from 1 to k. So that's just k factorial over lambda to the k. Okay, so that's the moment generating function. Let's do one more example. Let's do the moment generating function of the Poisson distribution. So for the Poisson distribution, we have that the probability that x is k is e to the minus lambda, lambda to k over k factorial for k equals 0, 1, 2, etc. So this is a Poisson distribution with parameter lambda for a fixed lambda. So let's calculate the moment generating function. That's e to the tx, right? Or the expectation of e to the tx. And by the theorem about the expectation of functions of random variables, this is going to be the sum from k equals 0 to infinity of e to the t little x, e to the minus lambda, lambda to the k over k factorial. And what is this going to be? Let's see. So how do we calculate this? Okay. So it turns out that what you can do is we can write this as the sum from k to equals 0 to infinity of e to the minus lambda, and then I'm gonna, let's see here. Oh, sorry, that's a k. That's a k. So we can combine this and that, right? And then that's going to give you lambda e to the t parentheses to the k factorial, to the k power over k factorial. And then we can move the e to the minus lambda out. So you're going to get this. And now this thing, right, this summation is just the summation of x to the k over k factorial, where k is lambda e to the t. And so this is just going to be, so you have e to the minus lambda, and then times e to the lambda e to the t. So this is going to be e to the lambda e to the t minus lambda. That's the moment generating function of the Poisson distribution. So we can use this to calculate, I think, the formula for the kth derivative. So the kth moment is going to be complicated. Or at least the kth derivative will be complicated. Maybe the kth moment is not complicated, but at least we can calculate, say, the expected value of x. So the expected value of x is the derivative evaluated at 0. So let's take the derivative of this. So it's e to the parentheses lambda e to the t minus lambda times the derivative of the top, and so that's going to give you lambda e to the t, right? And so this is going to be lambda e to the lambda e to the t minus lambda plus 1. No, plus t. Okay, so that's phi prime of t. And now we take the second derivative to calculate, say, the expectation of x squared. Let's just do one more. So what's the derivative of this? You're going to get lambda e to the top, and then times the derivative of the top. So that's going to be lambda e to the t plus 1. So now we can calculate the expectation of x. You just plug in 0 into your function for phi prime, And you're going to get lambda times e to the lambda minus lambda plus 0. So that's just lambda. And then the expectation of x squared is going to be what you get when you plug in 0 into the second derivative. And when you do that, you're going to get lambda e to the lambda minus lambda plus 0 times lambda e to the 0 plus 1. So you're going to get lambda times 1 times lambda plus 1, which is lambda squared plus lambda. So for instance, the variance of x, remember that's the expectation of x squared minus the square of the expectation of x. That's going to be lambda squared plus lambda minus lambda squared, which is lambda. So actually the Poisson distribution with parameter lambda, by what we've calculated, we've seen that the expectation is lambda, right? The expectation of x is lambda, and the variance of x is also lambda, which is kind of interesting. Okay, that's all I wanted to say about this video. So we explained what the moment of a random variable is, the kth moment of a random variable. We introduced the moment generating function, and then we've seen some examples of how to use the moment generating function to calculate the moments. And using the moment generating function, once you have the first and second moments, you can calculate the variance of x.